Alright, this is going to be a basic guide on building putting software on the DE10 Nano SoC, the system on a chip. So this is kind of for you, Dan. My guide does something similar, but the guide that you posted online does a little bit more. Yeah, so I'm just going to walk through it and see what happens, and yeah, we'll go from there. Let's see. So starting from the link, I think the first thing it has you do is set up the hardware on it, which really isn't too bad. The biggest thing, well, you also have to install this software, so you'll basically just follow these links and download it. And it's pretty self-explanatory. I already have it downloaded. I'm not going to bother with it again. Yeah, so with this, the one thing you want to note is you want standard, because we're not paying for Pro. And Windows or Linux, but I also do direct download. Akamai or Akimi, whatever, however you pronounce it, it's like an automatic download manager for you. I've kind of found it to be spamware. I don't really like it. I'd rather just have the download link and do it myself, so it's just a personal preference. Yeah, so right now I'm setting up the thing. I'm not going to turn it on because this chip does get kind of hot while you do this. Yeah, so what you're going to need, the way the hookup's going to be, and I'm going to do this in the way that it doesn't. So you can't see, but right now you have your board. You're going to plug in your 5-volt barrel jack, and you're going to plug it into the FPGA, but then you don't have to plug it into the wall yet. I would just get it plugged in and ready. And then you also have your micro, the mini USB, I think, the one that's bigger. I believe is the mini. You're going to take that and you're going to plug it into the UART interface, and that's right by the Ethernet jack. It's on the other side of the other one. The other one is for if you want to program it for the USB blaster, but we're going to program it for the HPS. The processor is going to boot up, and then it's going to program the FPGA. We're going to do that just because that way you don't have to have two of these cords, because it only comes with one mini. I have a second one, and I did testing with it, but I think I can get it working just the other way. Yeah, so that's not difficult. The thing about, you can plug that in right now, and it's going to actually recognize, because it gets power from, you'll hear the beep beep beep, it gets the power from the FPGA, well, the computer, I mean, it gives power to the FPGA. At least it powers up the UART interface, so it powers up the FT232 chip. It doesn't actually power up the FPGA, so I kind of misspoke there. And then the chip, or the M-select switches, this is how it tells you how it programs. So you can do just FPGA, you can do HPS, and the HPS programs the FPGA, and there's a couple other settings. And so you can see the user manual kind of gives you started and it gives you the basics, but this really tells you what you need to set the M-cell switches to determine how it's going to power up. So let's start with the user manual, and I can explain that. So the configuration, if you go on, off, whatever, it's FPGA gets configured from EPCS, and that's the flash. There's the FPGA on its own won't remember. It's non-volatile. It's not going to remember what's going to happen, what the memory or the bit stream data is beforehand. So the EPCS is flash, and it can configure from there. But we don't want to do that. I'm not really going to bother programming the flash when I can just have the HPS do that. So we're going to do, you can see there's two options for programming the FPGA with HPS, and FPP X32 and FPP X16, these are like different ways that the bit stream can be stored for the FPGA, and I'm just going to tell you how I did it because I know and I got it working and I don't really care. And I want to see if it matches up with that. So M-cell, I have the all on. So now if we pop over here, well, it's this one right here. But if we pop over to the actual guide, all on is actually off, so it's all zeros right here. And so it's FPP 16, compression is disabled, AES isn't disabled, which is a security feature, and it's fast. And that's what I got working. Now let's see what they did. They should be all on. Yeah, so that's what they did. They did all on. Now if you switch that up and then you don't do your bitstream file, I'll show you where it actually matters what you need to set it to. And if you want, you can play around with it, but maybe for a first step it'd be good just to do what I do. So set them all to on. The M-cell, they say what on is. on the actual switch itself, it's on. Yeah. Okay. So that's that. The next thing is this is the GHRD, is the Golden Hardware Reference Design. If you were to download their CD-ROM or just go online and get it, it's going to give you, it's in Demonstrations, SoC FPGA, and it's here it is, a Golden Hardware Reference Design. I started with that and I removed everything that wasn't essential because they put a lot in there because they want to test it all at once, but you know, when you're just starting off, you don't want to do that. So what I'm going to tell you to do instead, and just I want to be clear, this came from the Golden GHRD. It could you could have done this as well. So I have on my desktop, and I've put this on Slack, the DE10 Nano FPGA. So let's rename this because I already have a project named that, and I can go through everything. So DE10 Nano. Alright, yeah, so DE10 Nano _ blink LEDs. I recommend underscores over dashes because the project in Qsys Prime, Altera, won't let you use dashes, so it just kind of stays consistent. So let's rename that, and we're going to have to rename a bunch of project files, but also I'm going to put it to where I put my FPGA stuff. So you can see I've already done 2 of them. This one was a fail. But yeah, go in here, and I don't know of an easier way to do this, but what you're going to do is we're going to rename the project. And so what I'll do is I'll take this name and rename the necessary things. So take everything here, rename it. This back file, that's a backup file, you can delete it. I'm not going to bother renaming stuff I don't need to. This right here is the top level module, the Verilog module. These are the timing constraints. I don't know what QWS is. It's a good question. I'm sure it's something important. QSF is Qsys settings file, if I got it right. QPF is the Qsys project file, so this is how the project gets recognized. Summary, SImage, report, those are when it's built, those are reports for it. Not going to bother. I'll already rename that. And I believe that's everything. I'm going to delete that file. That file is not necessary. And a lot of these are output files. So just to show you, and you don't need to do this, is I'm going to delete everything that's not entirely necessary. So like you can see what we start off with and what gets generated. So yeah, let me delete those. Keep this file. That file needs to stay. We don't need that. We don't even need the summary file. Software that gets generated is doing HPS FPGA LED. You probably need that. I made that. We don't need that. That's generated by Qsys. Output files is also generated by Qsys. This, and this are a part of the Qsys project. Not necessary. We won't even touch it. So when you start to think about it, is take everything not highlighted. That is what I did, or what I've changed, and it's not a whole lot. It can be intimidating otherwise. So this, let me go through what everything is, and the Golden Hardware Reference Design kind of follows this. This is not in the GHRD, but it's another folder, and what it is the software. You can see there's a make file, main.c, main.o file, and then the 8 header file. So this is the header, that's the executable that gets put on the program, and so you build it on your computer just because you have all the include files and stuff like that. You have all the necessities, and it's easier to do on the computer and just to transfer it over to your FPGA, the HPS, I guess if you want to be technical. And the make file, that right there makes it. This is an object file. It's like a intermediate file before it makes that, and then this is actually the source file. SoC system, that's the Qsys file that kind of basically tells you how do you want to program and connect everything in Qsys. So it's kind of the fabric between Qsys and well, I mean HPS and the FPGA. It's the fabric between them. Yeah. This file right here makes this file. It makes the header, so you know you have to have the necessary includes and all that. Now we want to open some of these files. So I'm actually going to open like all of them in Notepad++, and let's edit them if necessary. So the QWS, don't need it. You can see there's nothing specific to the old project name. Let me copy and paste that. So I'm going to get the old project name. And you can see right here, we're going to rename that. So that's in the Q project file. We're going to name the project revision. I think that's the top level module. I could be wrong. I don't know what that is, to be honest. You can see the QSF settings files. It tells you your device. here's your top level entity, so I was wrong. This is what you want right there. And in your that won't, the next line down where the last addition in it, that'll change as you load it up and stuff, so there's no big reason to change that. None of this needs to be changed. Yeah, so the biggest part is the top level entity, so we'll close that. QWS, nothing important. SDC, nothing as well. So you can see it's just kind of basic. Now we do want to name the top level module, rename it, because it expects it to be the name of the actual module itself. Nothing else needs to be changed there. Right here, yeah, top level entity, we want to change that. This is in the QSF file, another settings file. Okay, now we're good. So now we want to open Prime and open it, and hopefully some of this stuff will be included. And as I said, I don't know if there's an easier way to do this. That's really not even that terrible to do, but okay, so yeah, here's our hierarchy. You can see over here, if I double click this, you can see it comes up with the .v file, so that's good news. Let's scroll down to files, and here we go. Look, we have our 4 files. That doesn't exist, and that's okay. That was in the output file, but I deleted it to show you things. So let's go ahead and remove that. Quip file, I'll show you what that is in a second. .v and your oh, I know why. It's got the weird, these are the old file names. I didn't realize that. So the way I add files, as I go and right click there, you're going to click the file name. Let's do Qsys first, and I'll show you what Qsys provides. So you go to Tools, you click Qsys, and this is where we're going to start to deviate from what I've done, because I used an existing IP, intellectual property, that Altera made called Parallel I/O, and what it does, it takes I/O, so in our case our LEDs, and those are the inputs, and it puts it a part of the bus. So the bus is the Avalon memory map bus, and you need to put it on there because you can't just connect those LEDs straight to the bus. You have to serialize them or parallelize them, however the syntax is for, or the specifications is. So when we're in Qsys, it kind of opens a default one, which are just like an unsaved. You can see up here one that doesn't mean anything. So Control O to open, but we can open the Qsys file. This does take a while. Saving kind of takes a little bit, a couple seconds, more than you're used to with like editors and stuff. And exporting to HDL does take a little while too, so that's something to keep in mind. Alright, this is what I've made. It's pretty much a bare GHRD. I took a lot out of the GHRD just because it's a little confusing to me. I probably still don't understand it, and I just wanted to work my way up. So we have our clock source, and you can see if you double click it, it's a 50 megahertz clock. And that's what you input, so it knows how to map it, because if it knows what the frequency is, it can do a divider to get it to a different frequency, because the HPS and all sorts of other things use different frequencies whenever you add them here, so it needs to know that. Clock input is exported, which means the FPGA, you'll put that in. So when you export something, that's the FPGA can connect to it. And then all this, if it's not exported, you connect it internally through this, and it won't be seen from the FPGA Verilog code. There's a reset input, and then these are the outputs. So think of it like as a block diagram. You have 2 inputs and 2 outputs. So it's like a buffer. It just takes the clock in, the reset, and it puts it out. And you can see in the description, this is an output, that's input. I added the HPS, which is the Cyclone 5. This is kind of why it's important to use the GHRD, because it has some of the defaults for you. The most importantly being the SD RAM. It has this megahertz set correctly, the DDR3, the memory speed grade. That's because you need to set this, and this is special to the DE10 Nano, because they have specific DDR3 RAM that they put on there, and a part of the PCB they connected, and so these specs are the specs for the DDR3 RAM. And it even gets to the memory timing and the board settings. From what I understand, that's kind of like tested. It's just what can the board do as far as speed. And so that's kind of, you do some testing, some timing testing. I don't know how to do it, but you get these settings, and that's what we've used. Yeah, this is your F2H SDRAM interface, so that means the FPGA can directly talk to the DDR3 not directly, I shouldn't say, but it can connect, it can bypass the HPS and do it, but there is a small controller that handles that because it needs to sync between the HPS and FPGA. Other than this, the only bus I'm using is the lightweight HPS to FPGA interface with. That's because it's very easy. Not a lot of bells and whistles, but it's also slower. You can see it's 32-bit, but if I were to enable these other two buses, you can get up to 128. And this is kind of like your high bandwidth kind of buses, but no need for them here. We're just getting something basic working. And the rest of this is kind of disabled. The peripheral pins, the ones that are kind of required to get this working is you need your SD/MMC controller, because your media card needs this controller, so that way Linux can read, the HPS can read from this and actually boot from it. And you just kind of follow this. You can do this exact, you just want to set it up like that. And then your UART, because you need a way to interface with it. You can do USB if you wanted to instead. I don't think that would work, because you would need to hook up the HDMI and get the HDMI working. So by default, you really have to do the UART, because you're going to need a way to communicate with it. So HPS IO set 0, no flow control, which means when you turn on that controller, whenever you communicate or you connect to this USB pin, it's going to go to the HPS, and there's going to be drivers and stuff in the Linux kernel that's going to communicate with it, and that'll allow us to use the FPGA or the HPS. Alright, so that's this. Nothing needs to be changed. Well, I shouldn't say that. This is my, now let's go down here, or let me first do this. Memory, this is a conduit and it's exported. So this is, you don't really touch this. This is, you have some wires on the top level module of your FPGA, and you just route them straight to the HPS to this memory port, and you don't really do anything. It's, from what I understand, it's like a soft the FPGA HPS description is kind of like a wrapper, so you're just going to pass these pins, but they don't mean anything. They're just kind of going to connect to it, and then when Qsys Prime is going to do all the work and actually connect everything, so you don't need to do anything with that. And then the HPS IO, this is going to have your you're going to connect your UART and stuff. Once again, this is top level module wires. I don't know why, it's not like there's actual wires there, but on the top level module you have your HPS, you'll have the wires and outputs and inputs, and you'll connect them straight to this Qsys file, but you really don't want to use them. They don't mean anything. They're just they're not actual representations of those wires, because the FPGA cannot directly access those HPS wires without doing something special. So I've learned that the hard way. You have your reset output, because yeah, the HPS itself has a reset output. You could connect this to the reset in, but I think that gave me errors. I'm not entirely sure, so that's how I have it. I connected my clock, so you can see my clock's connected to there. You just kind of click that little dot right there. The data, not using the SDRAM data. As you can see, I'm not using the DDR3. I'm not giving it access, giving the FPGA access to that. Lightweight, this is the lightweight bus. I connected the clock, and you can see this is the data line for the Aximaster, and it's connected to this parallel I/O. So this is what is so this bus is the bus that I can communicate with the HPS, and so I can write some code on the HPS to say, hey, I want you to talk to this memory address, and so it's going to know to talk to this LEDs block. So let's explain that a little bit. You have your clock, I connect it, reset, connect to reset out, and then this is your slave, so this is like the output of it. So it takes just like I/O connections and it puts them on a bus, and then your external ones I have them exported because I'm connecting them to the FPGA. The cool thing to note here is you can see your base and end. This is the memory map address. It's a little bit off. It's an offset is one way to think about it, because your lightweight the lightweight Axi bus starts at some address, and then this is the offset from that, because you can have these addresses can also relate to the other two Axi buses, so the FPGA to HPS and the HPS to FPGA one. Okay, so there's that. Let's play around with this. I know I got this working, but we need to delete this and make our own. We're going to make our own module that emulates what the parallel I/O does, and that way we can kind of get a feel of what it's like to make our own IP module, and it'll pretty much follow the tutorial. The tutorial and I are going to diverge later on. When I was reading it, I did something different, something I think is easier. So here's creating a custom IP. So you start, we're going to go into our folder, blink LEDs, and we're going to add a new folder, IP, and then they did another folder, named it custom LEDs. So we're going to name our module custom LEDs. Yeah, just to kind of give you a general idea of how you would do this. It's not going to be a great example. So in here, we're going to want to copy and paste this code, and I'm assuming this is a system Verilog code from what I understand, and this makes sense. I mean, I can go over it basically, but we have a clock and we have a reset. Those are inputs, and then also inputted we have the address that we want to read from. So what's going to happen is we're the slave. So it's similar to I2C. Is the master tells us when to read and write. We just listen to it. So the master is going to give us an address. Why it's an input. It's going to tell us when to read, and it's going to tell us when to write. So these are just 1-bit signals that are going to be control logic. And then you have your read and write. So read is an output because we're going to be outputting that data when it tells us to read, and then inputs write is when it tells us to write it. And then output, we're going to output the LEDs. Output the LEDs means we're going to write information to, that's going to be an output from this module, and we're going to write those LEDs. So let's go ahead and save it. Yeah, here we go. My documents, I'm in FPGA, blink LEDs, IP, custom LEDs, and they named this custom LEDs.sv, SBV being system Verilog. Alright, so now from Qsys, we go to File, New Component. We're going to name this, our component is named custom LEDs. I think our display name is going to be custom LEDs. Created by, I'm going to put my name here. We're not going to do an icon, we're not getting fancy. We're not going to do documentation either. I get what display name is. This is what you're going to see from the menu. So we want to make this look pretty. We're going to do LED with the lowercase s because the acronym is LED, and then the S is just to make it plural. Yes. We're going to go to Files now. IP, Custom LEDs, SV. So this is whenever you're synthesizing it, this is what you want to use, and you can make it the top level module, or you cannot. Like you can have multiple files in here, and they'll reference each other, but you need to tell it which is the top level module, just similar to your FPGA design. Verilog simulation files, I'm assuming if you wanted to actually simulate in Verilog or VHDL, you could use different files because you're going to hook the parameters up differently. But that's about all I know about that. Normally you click Analyze Synthesis Files. Let's try it. They say you can't do that. Why not? Oh wait, hold on. You gotta go to Signals and Interfaces. Let's see if it did it right. Okay. Maybe you can. I don't know why he said you can't do System Verilog with that. It seemed to work fine. Let me check the things though. Yeah, it messed up a little bit here, but is that the worst thing ever? It is not. So conduit, end, named LEDs, it's read data. Let's see. So clicking on it, let's click up here and see. Conduit, clock, associated reset is we need to set it to reset. This all kind of makes sense. And then let's go to LEDs. Let's see what they did for that. Oh, they did nothing. Okay. S0 must have an associated reset. I'm reading that down there. So make sure, apparently you have to read this. You kind of want to read this, make sure you don't have any errors or warnings. But that was pretty easy. The big thing was changing that to conduit. From my understanding, conduit's just like a wire. So we want to, since we're going to route this to FPGA, we just want to make it like a conduit to route out. Okay, and then we click Finish, and then we click Yes, Save, and that's our component. And you can see it right up here, Custom LEDs. So we're going to drag, well, let's click Add right there, you can see we have no parameters, so that's fine, but now we want to do some connecting. So I want to connect my clock. I want to connect my reset, but I want to connect it to this one, the output one. Connect my slave here, and my conduit I want to export. Sorry. So now let's go ahead and delete this. And you can see it's almost exactly the same. There's nothing different. That's why it's going to be a little bit boring. Everything else should be repeat after that. The interesting thing is it goes 0 to 0007. I think it should go to F. I thought it was kind of memory aligned that I had to do that. So you can come up here to System and assign base addresses, and it'll do the work of doing that for you. And apparently that's valid. So that's entirely okay. It must have been the way the module was made for the parallel I/O. So I just did a save, and everything looks okay. Let me walk through this menu. There's this little snippet about the TCL file. I have to do that for the parallel I/O, but that's probably because their tickle file is already doing that. Let's see what's in the tickle file. Maybe I'll do it just to get it going. Why is that? Okay, so it made it right here. I actually want to put it in my custom LEDs. That's just to keep it organized. So let's see. What do I know? Let's do it just to be consistent. I don't know. I might do a little bit of research later on, but I just copied and pasted it in. Pretty much can keep it all the same, I think. That dash should be okay. I think this is all for the Linux kernel. Who knows if this is actually required as of now. We did that. So now we want to generate the hardware description language. So in Qsys, we're going to generate HDL. Verilog, that's what we like, and just keep it all the same. And that's what this SoC system is. So this SoC system folder is not necessary. It's going to get generated. So that was another folder I could have deleted, but I forgot about. Let's open the one that I moved. And if I have this right, I bet you the top level module, yeah, I think that's better. You can see it now. It doesn't have the path. The path was wrong because I moved it. It was going in forward too, but now it's not. So that was the ultimate issue, I believe. So Tools, Qsys, let's open this, and I think the remove dangling connections was the other issue. So you might need to do that as well, because that other connection was still, from the parallel I/O, that connection was still there even though we deleted the module, because we didn't delete the connection. And so you're supposed to do remove dangling connections. A little while. Okay, so it is done, completed with warnings, which are okay. Close that, exit out. Now, I want to do a word of warning here, is that there's two ways. The Qsys is separate from your FPGA, from Qsys Prime, I should say. So what you have to do is you have to add that to your project, because that gets generated in its own folder. You add it to a project, and you can add it to whatever project you want. Now you can add the Qsys file to your project, or you can add this QUIP, which is already the synthesized folder. So, but if you add Qsys, whenever you hit run to compile your project, it's going to compile the Qsys thing, and the thing we just waited for, it's going to do every time you compile. I don't recommend that because there's some tickle file you're supposed to run, so you need to generate it anyways because you have to run it before you have to run the tickle files before you program. Alright, so come up here, right click, add or remove from project. You're going to go into here, select SoC system. This is where it got compiled. Let me change the filter to do that. So you can see it's not in here, it's under synthesis. And you can see there's your QUIP file. And that's already been added for my case, but you'll click OK. And it's an IP variation file, so apparently what it stands for, Qsys IP file. Alright, so that's added. And it's going to be a little bit different from what I have already, but it doesn't hurt to know how to do it. So generate show instantiation template, and you can see here is what you would do, and it kind of gives you a template. So hit copy. I'll just minimize that because maybe I'll need it again. And you can see you can just kind of paste it in. It's going to look essentially like what I already have in here. SoC system. This is the instantiation, and those are the pins. I mean, the only difference that I have is So you're welcome to change all these if you want. So let me explain how they get connected, and this will make a little bit of sense, but I'm not going to bother changing all of these. So here's your clock. Your reset is down here. Here's your memory. So that's that would be like I think that's like the DDR3 memory. It's down here too, but it's not the actual pins. It's like a metadata or some way that Qsys just knows that, hey, you're hooking this up to that, and it'll know. Well, here's maybe what I think is, with these pins you assign what the timing constraints are. So you say what the standard is. So say it's like 3.3 volts CMOS, and then you give it some timing constraints for those pins, and that's what gets connected. But it's not the actual pin because you don't assign it anywhere. It's just giving you constraints to it. SDIO, that is your MMC, that little micro SD card. You can connect those pins. Same idea, nothing actually there. It's just that, and you have your UART. LEDs read data. This is actually, you're going to input the LEDs, and that's going to work. So now if you look at the top level module, you can see here's our 3 clocks. The DE10 has 3 clocks. And the clock is actually a clock. HDMI, actually the HDMI connections, because that's on the FPGA side. But when you get to the HPS, there's all these connections right here, and we're not using half of them. But like right here is your DDR3 ADDR address and all of that. That's what you're going to connect to the SoC system. And the key LED and switch, those are actual FPGA connections. So it's important to realize that those aren't actual pins for the HPS, and you can't actually use them. So what I'm going to do is, if you want, you can change all that for a good exercise, but LEDs read data. I'm going to come down here, and I'm going to connect LEDs read data, and I'm going to connect them to all 8 of them. We're going to change that. I'm actually going to delete this commented out code because I was playing around and it didn't work. I learned a little bit though. So everything else here should be the same, but you can check, and it will probably check out if I'm right. Otherwise we'll see an error in a little bit. So yeah, we connected that to the LED, the 8 bits of the LED there, and we're also going to get rid of that because I was using those pins for something now. So we're going to use all 8 LEDs, and we can make an 8-bit LED counter on the software. Okay, so that's that, and so that's how that gets connected. So hopefully that makes a little bit more sense. So I think I know what the issue is these scripts can't be run before you do the analysis. From what I understand, they're going to get messed up in the fitter. So the fitter is going to run incorrectly, but the analysis can be fine. Because the fitter, you need the tickle scripts run to kind of constrain the pins, as I said, and that happens in the fitter. The analysis is just analyzing the design. So let's go ahead and run that file. Get that running, then we'll run our tickle scripts. Let's run some of these tickle scripts that are required. So if you go to Tools and you do TCL tickle scripts, you're going to see this pop up. Let me make it a little bit bigger. Might make it a little bit easier for you. Whenever you synthesize your modules, you're going to get some tickle files that you need to run. So SoC system, submodules, there's parameters, and you can see it was executed. So seeing this info box isn't a bad thing. It's what you want to see. And pin assignments. How it goes. You can see it seems to be thinking. I think it's going to work. Successfully executed this time. So close. I close that. Close the tickle thing. And I believe, well, let's see. I think we're just about ready to compile. Yeah, we are. Now we're just going to compile the entire thing. And this is going to take a while. Yeah, it's going to take a while. And then I'll show you the directory to show you what was generated, and we can go from there. Alright, we are done compiling. You can see all the check marks right there. So now the next thing is we have our SOF file. So let me show you what I am talking about. Here's this. Here's our system. And look at the files that have already been generated. Our Qsys file is already there, but you can see it makes a summary for the HPS. It makes the all pins text file. It makes the SOPC info file, which will be useful later on. It makes this pinned up. And then as far as this goes, it makes the HPS initial software handoff folder. So this is going to be our preloader, which will be coming on in a second. And output files. If we go into output files, here's our SOF. That is the final thing. That's what you would load onto the FPGA. And that's good if you're using JTAG or USB Blaster, which uses JTAG to interface with it. But since we want to put this on a file, we want to put it on a file in our Linux system or in our SD card and have that be loaded by the HPS, we have to convert it. So file, convert programming files, and it's going to expect a RBF, a raw binary file. And here it is, it's going to be output file, RBF. I'm going to put it, good, that's where I want it. But I think I'm going to name it, I want to name it the same thing as our project, or no, sorry, SoC system. RBF is what I want to name it. And then this is where we got to be careful. We want to select passive parallel x16 because this is why, this is right here, the mode, that is what we set our MCell pins to. So that's what you have to make the connection is you can play around. You can do passive parallel x32, then you need to go and see what MCell pins you want to select. But the other thing is like you have to worry about compression, you have to worry about if it's going to be fast or slow mode, and I don't know a whole lot about selecting that. I just know I got the X16 working. So if you want something to work, do that. Come down here to SOF data, input files, we're going to add our SOF file, output files, here's our SOF file, add it, and then basically just hit generate, and it's as simple as that. It generated successfully, close this. Now if I show you, it's in the main page. Here it is, SoC system RBF. And we are good with that now. So let's go back to building embedded Linux. Let's see, do they have you do the same thing? Same thing. So we're good to go there. Alright, now this is where it gets a little interesting. And this is going to be a little bit different. We're starting to diverge from what the guys did. So whenever you download EDS, which is the embedded development suite, a system on a chip, and there's a command shell. So whenever you download EDS, you get that. It's a special form of Cygwin for, at least I know it is for Windows. I'm sure for Linux it's just has their own sets of files and stuff that are run. Alright, so now we have to run some things. So let's start with BSP Editor, Board Support Package. So we're going to start with that. You click that, something's going to open up. We're going to do File, New HPS BSP. But before that, I want to make this bigger, and then we'll select it. Preloader Settings Directory. This is where you select your... so let's go to your project. Crap. You can't press the enter key. They don't like that. Blink LEDs. HPS ISW handoff. You're going to double click that, but not change the name of it. And you're going to select this. So by default, Qsys generates this file, and these are your preloader settings. Yeah, and so you're not going to change this. This is U-boot SPL preloader. Version default, and this is what it's going to generate. It's going to generate software, SPL BSP directory, and then this is where the file is going to be named. So let's press OK. Now, just to give you a brief overview of what happens, when the HPS comes out of reset, it has hard-coded in transistors that cannot be changed, a ROM that tells it how to boot. So it's very equivalent to a BIOS. The BIOS is hard-coded right into your computer. You cannot change the BIOS. And then the BIOS loads the operating system, which can be changed because you can do Linux, Mac, blah, blah, blah. So that's kind of the way that works, and it reads the MCell switches and it determines how to boot. And that's about the extent that I know and about the extent you need to know. And then that loads from the preloader, and the preloader is this right here. We're configuring it. So we're gonna, from the preloader, we tell it to do U-boot. So this is our preloader. This is telling it to get set up, and so the preloader is in charge of connecting to passing on to U-boot, which is the next booting way. And U-boot's just one option. You can do it a different way if you wanted to make your own boot thing, but preloader just goes, it passes itself on to something, to the next booting process, or however you want to do it, because there's multiple stages. And then the other thing is it has the HPS pin configuration. So there's a file in there that says, hey, these pins are going to do that, those pins are going to do this, like that little muxing thing. So this is what's going to turn on the SD card, it's going to turn on UART, and it's going to turn everything else off. Let's say you had Ethernet on, it's going to turn that on. All that stuff we did from Qsys for the HPS parameters will be in here. And the only thing we're going to change, just to kind of get this working, because I don't know a whole lot about it myself, is we're going to do FAT support. And that's for the booting. So what's going to happen is FAT support, it means it's going to look for uboot.image, and it's going to load that from the SD card, and that's going to be how it looks for uboot. Go ahead and save that, so Control S. Everything else is fine. You can change other things if you wanted, but that'll be fine, and then you generate. And you can see that doesn't take any time at all. So from there, let's exit out. Now BSP editor is done. Yep, right here, step 14, navigate into software. So LS, first we gotta actually get to, sorry, you have to go to your, oops, oh no, sorry. You have to go to where your project is located. I'm trying to think where it's at. There we go. Alright, so here's our directory. Now let's go into software, and then let's go into SPL BSP. And here, this is generated by you, or generated by the preloader in the previous step, the BSP editor. And now this is pretty simple. You hit make, because there's a make file. Sigwin knows what make files do, and that's gonna build uboot. Okay, so you can see everything went fine. I might have misspoke earlier, but I'm not entirely sure what this makes, because the next command is make uboot, and that might not be right. I can't remember if there's a dash in uboot. There's not. So make uboot, all one word, and this will make uboot. I don't know what the previous command does. Maybe it just retrieves uboot, kind of builds some stuff to get it ready, but okay, you can see that's done as well. Okay, so now it looks like the next thing is you want to take your micro SD card from the FPGA and you want to put it in your SD card adapter and put it in your computer so it'll be read. This is specifically for Windows, and I haven't played around with it on Linux yet. I know it's very difficult to read non-FAT file systems on Windows because FAT is for Windows, so I actually didn't touch the SD card. In this guide, they actually rewrite the SD card completely. I don't even touch the way the partitions are made, I just update them. So we can do that to start out with, and then I'll experiment a little bit more. The first thing to note is when it's plugged in, it's G, drive G. So we'll start with this. We're going to put the preloader on there. So, alright, so we're basically just going to follow this text here, nothing crazy. Alt boot disk util xe.p, which means and then we're going to put the preloader image on there. And we're gonna write it, so that's what that means, and we're gonna do the drive G. So this preloader is gonna load it. Now we want to copy some of the files to the FAT partition drive, and this is going to be your uboot image, and also it's going to load your FPGA system. And we're gonna put our code on there for that. So I'll show you one thing. It probably isn't necessary, but let's go into the HPS FPGA code. And now here is where if you wanted to edit the code and make changes, you just hit make and it'll make it. In my case, okay, so I did make clean to remove it. Now if I do make, it's going to build it, and you can see it made that file. That's something you need to do. It comes, I already built it, just whenever you download this, but if you do want to make changes, that's how you do that. Yeah, so now we need to copy that. So if you follow these three things, uboot, SoC FPGA, uboot.image, and then sig drive G. That copied. Copy, and then this gets a little crazy. That gets copied, and then I'll show you how you can do this. You really don't have to do this from the command line. And you can see this code changes a little bit here because I had it stored somewhere else. The point is you want to get the raw binary file onto the SIG drive, and in this case you want to name it SoC system to RBF because that's what it's looking for. So now the thing that Windows recognizes is it recognizes the FAT partition. There's 3 other partitions on here, I think, and they're not recognized. You just get this. So the Linux, all the files are on this SD card, but Windows can't recognize it because it's X'd for file system. So that's unfortunate in some ways, but here is, you can at least drop, here's our code, our executable that we built, here's our BF file, and then there's the U-boot image. Sync. I think I did everything, didn't I? Yeah, let's run sync. Oh, you know what we forgot to do? Crap, I should have done that. We forgot to do this. So, run generate. Yeah, this is something we forgot to do. So, if you look at this file right here and here, you can see that in my case the path didn't include something for this sopt create header file. So I had to copy and paste that and automatically do it. And now if you run this, it'll run fine. So you can see it created that. And this is going to change things because we did some changes. Let me close that. We made some changes here. So you can see it put it there. So let's copy, put it in here. And then I think we're going to have to change main a little bit. Let me see. You can see it's custom LEDs base, custom LED span. So it's just the macros that are changing, and that's what's going to make things interesting. So the code has a lot of printfs in it just to make sure you know what's going on. But this base, anywhere you see an LEDs, you want to basically add a custom LEDs. Which that looks like it's only the only place. And now since we're doing 8-bit, if it's greater than equal to 256, it'll reset. So it's going to count all the way to 256. Reg span, I think that's going to be okay. So now let's go in here. I'm sorry. Now let's go in here and see and make it. Oh, make. It made it. Now we want to go back to software, and I want to copy it. I'm just going to look for that. There it is. Copied it. Now let's sync our changes. Everything should be okay here. It synced it. It's just going to sync it. Take the SD card out. Take the micro SD card out and put it into the system. So I think we're just about ready to try it. Alright, clicked it into the system. We're connected. I mean, this is basic stuff. If you don't know how to do this, you're going to do a Google search. But if you go to Device Manager, you need to know what COM port it's in. And it's 11 for me. So I'm going to go to PuTTY. And I already have my DE10. And it's already set to port 11, and you can see it's connected, and that's because I have it plugged in. I have it plugged into the USB port, and it's powering it. Now I'm going to put the power on, and it should boot. So let's try it. You can see, look, everything's fine. Now, right now, this is U-boot, so now it's going to actually try and do everything. It loaded up SoC RBF, and this will take a second, but everything in theory should work fine. The login is root. And here we are. Now this is going to get a little interesting. I forget exactly how to do that. Here we go. Let's just let them do that. I already have it written out. Okay, so let's make dir /mint fat. So this is just going to be, we're going to mount. Oh, it already exists in my case, so I'm sorry. What do I have in here? Nothing. So nothing. I have 2 fats actually, but that's okay. So now if I go to dev, you can see right here there's MMC, which is the memory card, block 0, then there's 0 partition 1, partition 2, and partition 3. But let's go ahead and just mount this. I think it's going to be the same for you, but just mount that one. And it was not, it may be corrupted, but whatever, it's not, it's fine. And then let's go into there and take a look at what we have. And this is our fat one. So now we want to copy the LED thing, and we want to copy it to home root. Now let's go to home and root, and let's do HPS FPGA. Look, it's already counting, and your LEDs are working great. So there's the program right there. So let's cancel it. It's all working fine. Now, interestingly enough, we didn't have to do the device tree table thing. I did mess around with that, and didn't get... I know what I needed to do. I made a mistake early on. That's it for the video. Thank you for watching. If you have any questions, let me know.